Good morning, Randy,
Hi, Antoine.
and nice to see you again for this third episode and third session of discussions. So today I wanted maybe to touch a little bit upon the laboratory tests, and I would say what will be driving us during this talk is what is representative and how many tests do we really need before moving to the field. So with this in mind, maybe we can start straight away with the question, which is, which are the tests you think are very important to select and characterize the polymer versus what you think is less important?
Yeah, and as you know, that will depend greatly on the nature of your reservoir. Like, for example, the vast majority of existing, and I don't know, pretty much all existing large-scale polymer floods are fairly high permeability, not terribly high temperature, um, and cases that limit down a lot of problems for you, right? So that's one set of conditions is going after that. You also know that there's a lot of interest in the Middle East in carbonates, where a lot of the matrix rock is maybe less than 100 millidarcies, and they're hot and they're very hard saline waters in them. And their concerns could be substantially different than in these other types of reservoirs. So I guess that's the first question is you kind of need to find out where you are in that space. I mean, the questions in low permeability carbonates with super high salinity and temperature are, are some crucial questions that maybe just aren't terribly relevant for some of these high permeability sandstones with relatively low temperature and not that high a salinity. So I
So
mean, we need to focus on the area that we want to look at.
yeah, so
Yeah.
because especially in carbonates, you very often have fractures in addition to low perm, so dual porosity. But should we start with maybe we start with the sandstones and
Yeah. That's a good
the
place.
the
Right.
most, I would say, the most, not the most common reservoirs, it's not the case, but the places where people did start chemical EOR earlier. So in these sandstones, what do you think is very important to look for polymer selection and characterization?
Well, so again, the first thing I would say, which is often overlooked, is do you have a good idea of what your relative permeability characteristics are, and at least at a minimum where you think your endpoint relative permeability is, because conceptually and with a really good reservoir engineering basis, uh, having an idea of what the mobility ratio is in your reservoir plays a big impact on what's the ideal viscosity of your polymer solution to be injected. And so that's one of the first things to identify is, where am I? I mean, Daching's only maybe roughly 10 centipoise oil viscosity. Pelican Lake is 100 times that, right? So, uh, um, it doesn't make sense that you would necessarily have exactly the same polymer and viscosity for those unless there's something really interesting about the relative permeability curve. So that's important. I mean, the idea is to decide what is the an ideal place for you to be placing your injected polymer viscosity. That's a good starting point, I guess.
So that
Yeah.
would be basically viscosity curves versus salinity and shear rate. So
And concentration,
and
right? Yeah,
concentration.
exactly. Right.
So
Yeah.
because something probably important too is to understand if the salinity will change over the course of the project. Maybe the pilot no, but sometimes in some full fields the salinity goes from fresh water, river water to produced water, and so that's a different story that you have to.
That is a very good point,
Yeah.
and that also gets back to the mobility ratio idea. So I mean, if you took the position that Yeah, I don't care if I get a mobility ratio of 1. I'm going to settle for a mobility ratio even after with the polymer injection of 10 or 30 or whatever it is. Back even in the 70s, the Germans did some really good work and showed, on a field level that said, look, if I have a super good mobility ratio, or at least a mobility ratio of 1, and I'm getting a good displacement, if I'm getting, a reasonably good, maybe not perfectly piston-like, but reasonably good displacement of my polymer solution displacing my oil, and then I could keep my polymer bank intact. In their case, like in the Germans in the 70s type of time frame, they had really low, very high salinity reservoir, like 10% total dissolved solids in their reservoir. But the water that they were injecting was very low salinity, and they got the viscosity that they needed by uh, having a sufficient mobility ratio so that they kind of approximated a piston-like displacement. And so that's something they took advantage of and did a really nice job of demonstrating. If you take the opposite approach and say, well, I'm too cheap, I don't want to get a mobility ratio of 1, I'm going to just get something a lot worse than that, you're going to get viscous fingering. In other words, you're going to get a lot of mixing of your low salinity water with the high salinity brine that's in there, and you're going to lose a lot of the effectiveness of the solution, and your simulators are not going to capture that. It's going to fall apart. Whereas if you strive for a mobility ratio close to 1 and get a piston-like displacement, you've got a much better chance of your predictive capabilities working better for you. So, that's getting back to emphasizing you can't just ignore this mobility ratio idea. So,
And
okay.
so, because determined viscosity means putting a temperature and a shear rate in front of the viscosity we measure. So that's probably one of the only standard left in the industry, which is 7 reciprocal seconds. But in the end, people should try maybe to find out the real shear at the Newtonian plateau in the reservoir, because depends pretty much on anything like the spacing, permeability, porosity, and everything. So
Excellent point.
shear rate is
Excellent
one.
point. And just to emphasize on that, I mean, we do tend to get into this mindset of, well, 7.3 reciprocal seconds, and let's design the viscosity strictly on that. And as an example, Milne Point was a good example. They went into that thing, okay, let's just go for 7.3 reciprocal seconds. That's where everybody starts. And they did the initial design. And then after realization, just like you say, they're using horizontal injectors and producer up there. And the velocities in your reservoir are much, much lower than this effective 7.3 reciprocal seconds. 7.3 reciprocal seconds initially came out, 50 years ago, because some folks said, well, we're going to probably have 10 or 20 acre spacing. It'll be a 5-spot pattern, maybe 1 Darcy type of permeability. And when we look in our Corefloods, what's the kind of equivalent shear rate in the reservoir for that circumstance, equivalent shear rate? And it came out like 10 reciprocal seconds in that type of range. And 7.3 was a nice convenient spot on the
The Brookfield,
Brookfield
6
viscometer, and it
RPM
was
ideal viscosity.
nothing more sophisticated than that. So,
Yeah.
I mean, a realization that, like, in your real reservoir, that your effective velocity or shear rate is maybe much lower than that. That's where your mobility ratio should be calculated, is with using that effective shear rate. And so, like at Milne Point, for example, the initial design on that was like, well, we need to shoot for this one particular pattern at 1,700 parts per million, 1,800 parts per million polymer. And, after not too long, we said, well, geez, we can do just fine with 1,200 parts per million. That saves a lot of money, right?
Oh,
So, I
yeah.
mean, just that realization makes a big difference. So, yeah.
So we start with viscosity curves. That's just the right shear rate and concentration at the salinity, assuming salinity won't change. So what would be the next important test in your mind?
So you do have to look at the permeabilities of your reservoir, and the key question is this polymer that I choose stand a real chance of actually propagating through the rock that I have? If it's a super high, if it's more than 500 millidarcies, which most of the existing reservoirs are, you can make a lot of polymer floods work. I guess I need to put in a caveat because the Chinese at Daqing have gone into testing what they say are super high molecular weight polymers, maybe 30 to 50 million Dalton or gram per mole type of molecular weights, whereas most of what we get in the West and we talk about is maybe 20 million molecular weight. And they've done work in different permeabilities of rock. If we talk about the normal 20 million molecular weight, and if we don't have something unusual about the lithology, I'm all my experience with a lot of different rocks says it's not going to have any problem going into 200 millidarcy rock, even 100 millidarcy rock, unless there's something special there. Whereas I know there's people out there giving kind of some disinformation that saying a 20 million molecular weight polymer won't even go into 300 millidarcy rock. And that just speaks of somebody who's never really done an experiment before and tested this. So you do have to know what the polymer will go through the rock that you have, right? So you have to be realistic and look at that. And so what it says is, especially if you're getting down towards the lower limit of that, if you're getting down to 100 millidarcy rock and maybe you've got a standard fairly high molecular weight polymer, it's worth doing some tests to see if it's going to propagate. And along with that, you might just as well get polymer retention values of basically doing a mass balance of what comes out versus what goes in, and how much polymer is actually retained on that rock, and is it really propagating effectively? If you're seeing plugging, if you, let's say you decide to inject at a fixed rate, which most people do, then and you see a continually increase in your injection pressure, it says there's a concern there. And either you got some face plugging, maybe it wasn't dissolved properly, or maybe you've got something, or maybe there's even the polymer is just too big for that rock. With that kind of experiment, it is really good to have at least one internal pressure tap so you can make a distinction between whether there is face plugging or whether you're actually seeing the material propagate fairly well through the rock. So that's a step, and there's a number of aspects of that I think you want to discuss here too.
Yeah,
So
no, but so the first thing is when choosing a polymer molecular weight, which is always a distribution. So it's also good to remind the people who might listen, that when we say 18 million Dalton, it's a distribution, it's a Gaussian curve, and you might lose a little bit as soon as you enter the reservoir, for instance, and something that we have to understand. But my question I have is, so would you have two different polymers, or how would you choose a molecular weight? Imagine you have a very heterogeneous reservoir, and when you plot the permeability distribution versus percentage, for instance, I have a 50% of 1 Darcy, 30% of 200 Darcy, and 10% or more of the rest, assuming we know the reservoir and we have good data. So would you choose the polymer just saying that anyway, if it's above 300 millidarcy, we can probably be very confident that it will go there? Or would you make some slight changes, especially by pattern, for instance, or by zone, depending on the understanding we have of the geology?
so it's a good question. One of the first things I would do would be realistic about what are my primary targets as a field operator. I mean, if I have and people do this naturally, even with water flooding, right? If they say,
Mhm.
here's a zone, it's 500 millidarcies. I know there's a good oil saturation in here, but then there's this other little zone. Maybe it's much smaller, maybe it's 10 millidarcies, right? So, so I have to ask the question, do I really want to go after that 10 millidarcy stuff? Is that practical for me? So I have to make a judgment on where my real value in that reservoir is. And maybe I have to write off the low permeability part. On the other hand, if the vast majority of it is, I don't know, let's say 100 millidarcies and I just got maybe a little bit that's 500 millidarcies, then my main target is in that 100 millidarcy area, and I need my polymer to go in and displace the oil from that 100 millidarcy. So it really boils down to that: is the operator has to make a decision: is where's my oil? Where do I have to make my target that I need the polymer to go into? And I make that judgment from that. If it's a 100 millidarcy zone that's got most of my oil, I'm probably going to have to compromise and use a lower molecular weight polymer and make sure I get in there and go after that. So it is a balance that's going to occur at that point.
So we said viscosity curves, shear rate. So the Coreflood will come back to them. And what would be, imagine now you have a hot reservoir and you want to choose between different chemistries, some containing ATBS, for instance. How would you screen these polymers? Would it be some long-term test, or will you be using Arrhenius flow, I suppose, from the beginning to try to understand what you can expect
Well,
for
I
stability?
would. What I would, first thing I would say is a lot of great work has already been done, and you want to use that for guidance, right? And the guidance says, even since the 1980s, is that if your reservoir temperature is below, let's say, about 60 degrees centigrade, polyacrylamide is going to be sufficiently stable for you. I mean, it will start hydrolyzing, but it'll be at a pretty slow process. Even back in the 80s, the people who had done these initial experiments said, yeah, you might be able to get away with 70 degrees centigrade, but it's getting a little iffy. And so, people being, cheap and trying to get the most cost effective thing for us, they've tended to say, well, I'll go ahead and risk polyacrylamide even at 70 degrees centigrade, just because I know that's cheaper than putting an ATBS on it. So it's worth a try. And I think the experience that the Indians have found in Mangala and those places is saying 70 degrees is just a little bit too hot for polyacrylamide. Now, when we start getting up,
So what, just for polyacrylamides without ATBS?
yeah, without ATBS, right?
Yeah,
Because that's what people are going to go for. They're going to go for the cheapest thing they can, if they
yeah.
can, right? And they're only going to use ATBS unless they see a really good reason to use ATBS, and because it's going to add a little something to the cost. Um, then I guess maybe doing an easy one, which is actually relatively recent and a super great development, is making these 100% ATBS polymers commercially available. I mean, that's a big step forward for us. And our work, we did Arrhenius analysis. We're big believers in the Arrhenius analysis, and that said that. We think we can make this work even certainly at 100 degrees centigrade, no problem. We think we can make it work at 120 degrees centigrade if you're talking about like needing it for a 5-year residence time in your reservoir. Now there's a big gray area between there, right? Let's say between 100 and 60 or 70 degrees centigrade. And the question is, what's exactly the right amount of ATBS to put in there to get just the right amount. Maybe some of the other folks have a real opinion on that. It does make sense that the more you put in, the more it's going to be stable it's going to be, but it's also going to cost more. And then what's the exact right number for, you know, a given temperature between 70 and 100 degrees centigrade? You know, I can't really say I know that. I would feel comfortable with 100% ATBS, but that's certainly going to cost some more.
For the rest, it will depend, of course, on the divalent content, the R plus and salinity.
Exactly.
So
Good
the idea
point.
would be
Good point.
to ask the chemical suppliers, because they run a lot of thermal stability tests on different brines, different field cases.
You know, I think,
yeah. So that could be
yeah.
a good start. And just to bounce back on your comment, so because in the hydrolysis process there is the question of time. So what about the residence time in the reservoir? Is it important maybe to understand how much pore volume we will inject? Because my point is, so two things I'd like to ask and maybe discuss. The first one is, imagine you have 5 years residence time into a very, very hot reservoir, but you plan on injecting just a portion of the pore volume just because you decided so, and the economics, you don't want to spend more. So that's your choice. But the question is, imagine injecting this pore volume will take 1 year out of the 5 years residence time. Then you switch back to water. So my question is, was it worth to maybe inject a very expensive polymer, knowing that in 1 year it will not have hydrolyzed? And anyway, that as soon as you resume water injection, what we see and tend to observe in many projects is you lose all the efficiency, and so you don't propagate the slug, you don't push the oil. So my question, in addition to stability and chemistry, is, does it depend also on how long you think you need the polymer to be stable in the reservoir based on your plan, which can be changed? But
yeah, excellent points. But let me make a step back just to make sure we get everybody on the same page. It is important for people to understand that the residence time that the polymer is going to be in the reservoir is an important factor, and that's a strong function of spacing. So I can, for a given injection rate, I can, you know, decrease that time pretty much in direct proportion to my well spacing. If I make a tighter well spacing, I don't have as high a requirement of how long the polymer needs to be stable. It says that infill drilling is an option to get around this problem, right? So that's an important thing to keep in mind. Injecting faster, if you can, is a way to get around this problem as well. But the key thing is to, as you suggested, ask your question, how long do I think the polymer needs to be stable for what I'm going to do? Okay, the next thing that we get to, which is a little different issue, is the issue of bank size. And this has been thought about since the 1970s, and especially back in the 1970s and 1980s, people had this concept of, I'm going to inject a small polymer bank, maybe a 10 or 20% pore volume bank, and it's going to magically only go into the high permeability zone. And then it's going to just lazily drift through the, I'm going to switch to water injection, and it's going to, that polymer bank is going to just lazily drift through the high permeability zone, and the water that's coming behind it is going to be diverted down into less permeable zones and push a bunch of oil onto my production well really fast. Okay, so and a lot of, you know, some really impressive people bought into that, and I think all of the really good laboratory information and all of our field results said that's just not going to happen. You're fooling yourself, right? And it's not what people want to hear, but the truth is we need to be injecting the largest practical polymer bank that we can, because all of our simulators don't, as a general rule, do a very good job of simulating the severity of water fingering through that polymer bank in the most permeable zone. What they don't pick up on is when you start injecting water, it's not going to be diverted down into the low permeability zone. It's just going to blast as effectively as it can through that high permeability polymer bank. That's where it's going to go. So this concept of a small polymer bank, I think everything we see says, I know you want to do that from an economic viewpoint, but it's not going to work. It's going to backfire on you. So that's
But
my
there's been
thoughts.
some evidence, I mean, from recent projects in Kazakhstan, in Oman, in Kuwait, when people just resume water injection, and you see that the efficiency is decreasing very, very fast. And there was even a mention into a paper from Oman saying that that's why also you need a very high running time of your facilities, because what they have seen is if you have a little bit of downtime and you have to switch to water, then right away you see the oil profile declining, which is just telling you that, well, now it's you have compromised the slug integrity. So, and
Excellent point. And everybody's seen that. Dacheng has seen that.
yeah.
Mangal has seen that. Right. So that's
And
excellent
so
point.
something maybe more complex, but if it's really to keep pushing in large banks, so what about injecting not one but two polymers, one after the other? Like the first one will be more stable, more resistant, and it will be at the forefront of everything. And once you reach basically half your protocol, you switch to something which is a bit cheaper, the same mobility ratio, same viscosity, but you don't expect it to be stable for a longer time because anyway, you have already absorbed the first in the first front and you can still displace one. And when you resume water injection, anyway, it's over. But so what about having not one, but two polymers? One more expensive at the beginning, more stable, less retention, a bit more ATBS. And once you think that you have reached halfway, say, okay, I want to decrease the cost. I have filled the rock with retention. I just want to displace a little bit my previous slug. I have the same viscosity. It's for instance, 25% cheaper and makes everything work. So I keep injecting and but a different polymer. So would it be something too complex? Would it work? Would be
I never thought about it, but my first reaction is that sounds like a reasonable idea. If you have the things timed out well enough. Let's say you start with something that's a high ATBS content, and that's the bank you need to have going for a long, long period of time. And then you say, let's switch to polyacrylamide or something with a lot less ATBS and something a lot cheaper. And you say, yeah, I know it's going to degrade, but it's not going to degrade before my more expensive bank gets out where it needs to go. I don't see a problem with that idea. It sounds like a good idea to me.
and so because also the problem we have, and that's why people in the very beginning were considering associative polymers, is they want to put less polymer to have a higher resistance factor. With the problems we know or that were at the time, like higher retention with associative polymers because they are amphiphilic. And since they are amphiphilic, you can create emulsion problems. But now, if you basically inject them at the end of the slug or towards the end of your polymer injection, you will have no retention, basically, if you have the same resistance factor, because the polymer at the front will
You're
have
going to be
absorbed.
injecting the thermal responsive or associative
No,
polymer, you're saying at the end?
the associative polymers, but at the end of the slug, like, the second polymer. The first polymer is the more expensive sacrificial one. And towards the end of the slug, to have lower concentration but the same resistance factor, considering associative polymers, without the drawbacks of maybe the emulsions and the adsorption, because the oil bank is already been pushed and the adsorption has been already, I would say, matched by the first polymer in the bank.
But which is the first polymer you're injecting? Is it the
Any
associative
what you were
polymer?
mentioning, like IATBS or ATBS polymer, conventional HPAM,
And then
something to
the thermal responsive associative polymer is being injected later. Is that what you're
yes,
saying?
yes, yes, yes.
Okay. Um,
It's just in a way to kind of decrease the cost for people who really want to keep pushing but have, economical issues. So it's the same idea as two polymers in the same front, one sacrificial, one less expensive. It's just even maybe the less expensive might be the associative because of its lower concentration, higher resistance factor. And without the drawbacks we've seen when people were using it all the time, like, in some cases in Canada, they were injecting associative polymers because they had very big conformance issues, but they also got some emulsion problems because of the associative polymers and very, very high retention in the same time. So just,
Okay.
sharing some.
Um, I don't have a problem with the concept. The practical reality of the associative polymers that we've had so far, it seems to me that most of them need significant additional development for several reasons. One, a big one is predictability and controllability. I mean, we have certain ideas of the ideal sorts of viscosity that we need in the reservoir. And if we're way above that, that's a problem for us because of propagation and injectivity and because they're associating, as you suggested, retention. I mean, if they get retained, that's a big issue for us. If they don't have sufficient concentration, if they get diluted or something and they lose their viscosity, become ineffective, and then I have maybe a viscous fingering problem. So controllability and predictability
Yes.
has been a big issue with associated polymers to this date. And I think the basic concept behind the associated polymer is great, especially the thermal responsive polymer. If we could do it reliably, I think that's got a tremendous amount of potential. But the problem is, one, predictability, controllability. Two, this retention propagation issue. Can we really propagate them? If we can solve them, that'll be a big plus for it, right?
So my experience when I was running Corefloods is it's much easier to inject them after a first polymer has saturated the core. So if you have a Coreflood and you inject a conventional HPAM and you saturate everything, when you switch to thermoresponsive or associative or whatever similar type, then interestingly, things get much smoother and easier than if you were to inject right away in the core. That can tell a
Um,
little bit about mechanisms and things like this, but so that was maybe the idea of using them, as a way to optimize the economics more than optimizing the full process and full cycle of the.
Yeah, if you have that worked out and a process where it says, yeah, inject a normal polyacrylamide first and it does some positive things that make the subsequent polymer less retentive, better ability to propagate, a lot more predictable. Yeah, I'm all for that. That's a big plus. That's great.
So
Yeah.
we mentioned viscosity, shear, selecting the right thermal stability. Do you recommend any degradation test? I mean, assuming that you expect specific things in the field, like, I don't know, I know you will say you should remove the oxygen, but if you expect some either mechanical, thermal, or chemical degradation, so do you recommend some test based on the conditions and the field specifics, or is it something that it's better just to avoid considering and to remove the problem?
Well, it's certainly important to be aware of what's a problem and what's a limitation for you. So a lot of tests have been done on acrylamides and a lot of different polymers. And we know that if there's no oxygen present, that's going to give you maximum stability for any of these polymers, no matter what it is. And the other positive thing we know is once we get in the reservoir, those are completely oxygen free. I mean, there's nothing down there. So the trick is we need to get it from the surface to the reservoir intact without having it degrade. And if we have a lot of oxygen that leaks in the system, and especially if we have iron 2 in our water makeup the polymer makeup water that we very often do. Iron 2 in the makeup water isn't a problem at all if there's no oxygen present. But as soon as there is oxygen present, now you're creating a mess. You're precipitating the iron, you're getting particulates in there, you're setting up a redox reaction, it's degrading your polymer, and it's lose-lose all the way around. So, there is certainly an issue with convincing operators that they can't be cheap and lazy with respect to oxygen. They need to have it at a controllable level. I mean, if you got super low temperature of your reservoir, and very important, and if you have no iron in your makeup water, you could get away with a lot. And a number of polymer floods have been able to do that. But a lot of people make the jump and say, well, Daching did it or Suriname did it. Why can't I do it? And the reason you can't do it, even though it's a low temperature, is because you've got iron in your makeup water and it's causing you all kinds of problems, right? So you do have to have that realization. I mean, we are talking about lab tests, but you do have to make sure your operator understands if they've got any iron in that water, or if they're going to pick up iron in their pipes or something while they're doing this. They're crazy not to keep this thing oxygen free. And it's not really all that difficult to lower the oxygen. Let me look at it from another viewpoint. A lot of people don't know how to do stability tests very well, thermostability tests very well. And, if you don't know what you're doing, it's very easy to get oxygen leaking into the system while you're doing these tests. And a lot of people have, if you just, company laboratory A's or Z or whatever, who's never done this before, and they start into it. And their first conclusion is, well, this stuff degrades after 30 days, even at a relatively low temperature. And that's not the right answer. You did the lab test wrong in that case, right? You got oxygen leak in, and it gave you an overly pessimistic answer. So that's why going back in the literature and says a polyacrylamide, pretty much most polyacrylamides, there's no good reason why they can't have pretty darn long-term stability, like years at 50, 60 degrees centigrade. If you're seeing degradation after 30 days, you really ought to be saying, maybe I'm not doing my lab test right. And you don't want to give a pessimistic answer like that to your field guys, because you just did the lab test wrong is what's the problem there. So that's a reality. I've seen, I just watched a video of a simulator saying, okay, yeah, we got a lot of people who did laboratory tests and they saw degradation after 30 days. And we just ignore that in our simulator because we don't believe it. Well, you're right. You shouldn't believe it. It was obviously a case where they didn't do the test right. The other side of it is people who do a test for 30 days or 60 days and say, well, I don't see much viscosity loss, so therefore the polymer is stable and it's going to be stable for 10 years or whatever. That and which is a mistake too, right? That test doesn't mean anything. That's why I'm a firm believer in, if you really think you're dealing with a relatively high temperature, you need to be doing an Arrhenius analysis, because it's the only tool we have for long-term projection of it. Whatever things you don't like about the Arrhenius analysis, it's the only thing we have for making that kind of projection. That's a little bit on oxidative degradation. Key number one, convince your operator to get the oxygen out of the system. If you're doing a laboratory test, you're probably wasting your time unless you get the oxygen out of your system. So those are important things to keep in mind.
Also, just to add something on this before you move to the next one, which is removing the oxygen in the field, but remove it right. What I mean is, if you remove the oxygen using a scavenger, for instance, but after you have an excess of scavenger and you have oxygen coming in again in the stream, then you're back to no viscosity and you've just degraded the polymer. So
Good
removing
point.
the oxygen is nice, but you have to make sure that after there is no other leak. Otherwise, you spend money for nothing. So it's also quite important, I think.
Yeah, that's a good point too. And we certainly don't have universal agreement out there in the industry on this. My personal, very strong belief is we should do everything we can physically without chemicals to keep our oxygen content low. And then at that point, if we decide we absolutely need some oxygen scavenger, we can start adding it. But chemical oxygen scavenger is an expense. It does raise some other complications, just as you said. If you remove the oxygen, you put in one of these oxygen scavengers in there, chemical oxygen scavengers, and it somehow gets re-exposed to oxygen later. You set up another redox system, and that's even worse for degrading your polymer. So you got to be careful with that. So that's for all reasons. I really emphasize do everything you can physically to prevent that oxygen leaking into the system. And as starters on that, if you've got a source water that's coming out of the ground, there's two probable characteristics of it. If it's coming out like from an aquifer that's moderately deep, number one, it's going to be oxygen free. And if you do the test right, I've never seen a case where it's not oxygen free. Okay, in all these different reservoirs. Number two, it's probably going to have some iron too in it. Okay, if it's a reasonable subsurface aquifer, and and that's not bad. It's not a problem to have iron in there, but you gotta keep the system oxygen free. If you don't, naturally iron too, and it sees any oxygen, it's immediately going to start oxidizing, right? And okay, so what can you do? Well, number one, be careful on your tanks. Just the key message on all of this is don't let oxygen leak into your system. I mean, and do everything you can to do that. Go through your entire system with a little oxygen meter and find out where that oxygen wants to leak in. A big place is tanks, right? If you the standard thing with a tank is you bring water over and it comes into the top of the tank and it falls down through some kind of atmosphere, which is probably air. And of course, there's a lot of oxygen in the air. So you're just oxygenating the heck out of that, right? Which is defeating the whole purpose of what you're doing. You can do a massive amount on reducing oxygen coming into the system if you don't have that water inlet in your tank just spraying over everything and picking up oxygen. If you actually can have that flow stream enter the tank below the surface level of the liquid, and of course maybe have a check valve so it doesn't go backwards, but have it come in there, you can massively reduce the amount of oxygen that goes into that.
You have
Another
the
point. Yeah, go
equipment,
ahead.
nitrogen blanketing equipment.
Yeah,
Uh,
so nitrogen blanking equipment is good and what I think excellent. And I know people say, well, that nitrogen is going to cost me, and especially if I'm losing nitrogen and I go through a lot of nitrogen, there's a high cost with that. So I need to minimize that. And we're getting a lot better with our designs at doing that. Like one of the most recent designs of the polymer hydration tanks is a big step forward from what we had in the past. We had, you basically got one big tank with, baffles between them, and then the polymer after it's being sliced or sheared or whatever, the polymer powder, it comes into that instead of being pumped from one tank to another. It's got just one big rectangular tank and it's maybe going through 5 compartments for hydration, and you just all you have to really do is have a nitrogen blanket on the top of that thing, so it's very limited nitrogen introduction, and you
Consumption,
don't
yeah.
really have consumption, don't have a lot of losses. So I mean, with designs we're having are getting a lot better so that you're not consuming a lot of nitrogen. Another really good idea that's been implemented, a big source of that oxygen could come in is if you've got like a hopper and you've got your powder in it, and it's coming down either into a slicing unit or some kind of adductor or something. And there's oxygen within those grains. Well, it's a tough thing if you say I'm going to just have a nitrogen blanket on the very top of that. You're going to be going through nitrogen like crazy. So instead, the really good idea is to have a nitrogen introduction feed pretty much at the bottom of the tank or in the slicer or the hydration unit itself. So what it's doing is it's got a continual nitrogen push that's always pushing upwards. And at the top of your silo, you've got high oxygen content in it, but you're always pushing that oxygen away with the nitrogen as you're putting it, and your nitrogen consumption then is really not so great. So that's a really good innovation as well. So the bottom line, we're getting a lot better with our nitrogen. So we've got less and less excuse for not keeping the hydration equipment oxygen free, right? And it makes a massive difference. We can I mean, but previously we've seen massive losses of polymer viscosity and therefore money because of oxygen degradation in the system. And we do have the ability to not be so bad about that.
Something, I mean, to come back to the lab and the oxygen experience I had, that when you are running Corefloods in ovens and conventional systems at very high temperatures, there was also oxygen leaks within the oven and the Coreflood systems. Like if you have nylon, if you have something porous, if you have a valve that's kind of leaking, if you have anything like this. And I've seen cases even during Corefloods where you would see the pressure drop decreasing in the next pressure tap in the middle of the core, which was quite surprising at the time. And we were mentioning, for instance, at the beginning, the thermal stability studies, and sometimes people who don't know how to run them. And I would even probably be more, I would say, cautious about all the lab tests, because experience show that depending on the operator, sometimes you have leak into the ampoules, the sealing, you have
Oh
iron
yeah,
in the
yeah, exactly.
ampoules, you can
Yeah.
have iron in the membrane used to make deionized water, you can have iron in the salts and NaCl depending on your supplier. Sometimes even the air conditioning in the lab will impact the pressure drop in the core if it's outside and goes up and down with the night and day. So it's really the fact that first it's quite, you should know what you're doing when you do some lab tests for sure. Then the operator should not change too much, or at least you should be able to compare. But I think what's worth is, well, apart from the API RAP 63 that exists, there is really no up-to-date protocol to run any of these things. And when I read the papers, sometimes it's difficult to draw conclusions, because the way you restore the cores, you saturate with oil, the pore volume you use, the way you prepare the polymer has an impact on the results. And sometimes it's a bit, I would not say scary, but it's a bit strange for people to draw conclusions based on a study and to say that the other person was wrong. Because sometimes if you use two different sets of, I don't know, rheometers or core holders or cores or even filters in the filter ratio, you will have different results. So maybe I think something that should be, again, really thought would be to have updated protocols and understand the variability even within the same set of filters, equipment, and these kind of things, because it has an impact. And to maybe continue on what we're discussing with, so rheology curve, shear, oxygen, what do you think would be another test? So what do you think, for instance, about screen factors, filter test, and what could be their purpose? Are they underused, overused? So what are your thoughts about these tests?
Well, okay. So first of all, you're right. We have a lot of different laboratories company laboratories, service laboratories, and they often have very different views on what tests to do. I mean, that's a reality. And another reality is that probably every lab has things that they're really quite good at and they know very well, and other things that they're not good at. And that's certainly been an issue for us. Is, I know when API 63 came out, the idea was to establish something uniform. But even at that time, people fought like crazy and said, this test is worthless and this test isn't, so there's big differences of opinion. And some of those differences of opinion come out because certain criteria, certain things are really important in some reservoirs in some circumstances, and they're not important at all in others. And so my ultimate point is, I don't know that we have a solution to that yet. I know there's one country in particular, the Chinese, who had said, why don't we just get together and have a number of people establish a big new criteria. The problem with that is then you get into politics and somebody saying, well, you got to use my filter test and this is the only right way to do it. And a lot of other people say, I don't think your filter test is worth anything, so why should I do it? So, it's going to be tough for us to get agreement on some of those things. To go back to the point, go
would
ahead.
there be some things which are more representative of what might happen in the field? And for instance, I don't know, let's say, okay, even though retention and in situ rheology will depend on lithology and permeability, if you get the values right for one lithology and one permeability, we should normally reasonably expect to obtain very similar values for all the same lithologies and permeabilities. So something we obtain at the right shear rate in the right conditions in the core normally should be upscalable with some limitations to something in the field. But for instance, let's say, I don't know, a residual resistance factor test or some filter test that we run on the pristine model solution in the lab versus the polymer solution in the field after going through the pumps, for instance. So maybe in some cases, it's just a question on where and how to apply. And in some other cases, it's maybe the relevance and representativity of the test itself, like, for instance, residual resistance factor.
So let me deal with that. I have a very strong bias that the viscosity that you measure under conditions that are pretty representative of the reservoir, let's say temperature, shear rate, salinity conditions, that viscosity is very important, and you should pay a lot of attention to that. Now, beyond that, there's a step in what happens in porous media, and we have very different beliefs out there. We have some people that believe that, and for a long time, Dow pushed this idea back in the 60s and 70s that, boy, you're going to get this incredible residual resistance factor. There's absorption on the rock, and it gives you a lot higher mobility or a lot lower mobility than you detect just from the viscosity. And we did I think we knew even in the 80s there was a serious problem with that thing. And then it was because, if you don't treat your polymer right, you've got super high molecular weight species within that polymer, which are never going to propagate deep into the formation. Your question as a laboratory guy, as a field guy, is what is the effective viscosity of my polymer going to be deep in the reservoir where the vast majority of the oil is being displaced? And what can I come up with that is representative of that? The viscosity measurement's a pretty darn good measurement. I got a good physical basis for saying, well, it ought to be about that if I can keep the thing stable. And if you start taking the position, I'm going to get a lot of residual resistance factor permeability reduction, we have proven over the course of the last 40 years that there are just terrible artifacts you can get from cores that can badly mislead you. So, I mean, we even have people in the simulators today. I just watched a video where a simulator guy was saying, yeah, no, look for a residual resistance factor up to 5 is okay. No, it's not okay. If you see anything more than 2, you're fooling yourself. That's crazy. You're not going to get 5 unless you get serious plugging. If you get serious plugging, you're not going to have any significant polymer propagation through your core. So you're fooling yourself if you think you're getting that kind of residual resistance factor. Okay, so artifacts can lead to those things. Now, it's tempting why people want to see that kind of thing. I mean, the higher my residual resistance factor, that means the less polymer that I can
I
put
can
into
use.
the
Yeah.
reservoir. I don't have to have as big a polymer bank. I can use lower polymer concentrations. But if you're just fooling yourself and you're just making a process that doesn't work, that's not a very good thing.
No, but I mean, plus what's happening in the core, it's something we will touch after on the core flooding. But so you have a still unstable displacement when you displace the polymer in the rock at the fixed rate, and in the reservoir, you will still do much more damage to the low perm zone than the high perm zone. So when the water will go back,
Exactly. That is a really
yeah,
key point,
when the water will go back to when you resume water injection, I mean, the pressure drop in these low perm layers is so high that the water will never go there anymore anyways. It will just finger through the hyperm zone. So it will
that's an
just
excellent point.
recirculate
And we,
water into hyperm zones, which is where
yeah.
basically the radial resistance factor will be very low because the damages are still even much lower in the hyperm zone than they are in the low perm zones. So
Yeah, we don't want to gloss over that because a lot of people miss that. They get excited about a high residual resistance factor. And the reality in pretty much all the cases we've seen is if you're seeing a high residual resistance factor in some rock, let's say a high permeability rock, whatever, you're going to see an even higher residual resistance factor in the less perm rock. And that is going to have a very negative effect on sweep efficiency. It is not going to help you. A lot of people miss that, and that's a crucial point. That is a
but
really good
but
point.
but plus also this is what we were discussing in the beginning. So if I think you really had a very high residual resistance factor, the moment you switch to water injection, you should have some resistance. You should not see the oil collapse. You should not see the water cut going back to where it was before polymer injection. Otherwise, it means that you have destroyed everything you built in the reservoir, which is more likely that just having resistance. Because also something I see when people input residual resistance factor in simulation, it tells them that when they switch back to water injection, they will get some extra oil because the water will be diverted or displace oil in zones that were maybe not be that have not been swept by the polymer, which is not what we observe at all. In many cases, when you go back to water, it's over. It's like the oil rate is going down, to the floor, and the water cut is very fast increasing again, and you lost the efficiency. You see some polymer breakthrough, and then boom, just the water, and you're done. So it goes, I think, against the field evidence, what we see, this RRF story, I think.
And it goes against the lab evidence too, right? I mean, so to kind of say it again, what you've said very well is, well, I'll just say it. A high residual resistance factor is not a good thing, right? You might think it would be if you had a perfectly homogeneous reservoir, you could convince yourself it is a good thing. But since we don't have that, the high residual resistance factor, number one, you're not going to get it. Number two, you're just fooling yourself if you think you're going to get something more than 2. I'll buy up to 2, right? But anything more than that, yeah, it just means you just screwed up the experiment, or you're dealing with low permeability rock. And what you're basically doing is the polymer is not propagating very well in that low permeability rock, which basically means you're writing off the oil that you might get from that low permeability rock. You can't miss that point. So, yeah.
So it's a good transition to Corefloods. So when it comes to Corefloods, what will be the important parameters, what you would look into? So for instance, propagation, retention, in situ rheology, what would be the size of the core with oil, without oil? What kind of protocol would you think are important and useful for retention, for instance? So, and You mentioned internal pressure taps, so one is enough, two. So what are your thoughts about the core flooding as a whole?
So it depends a lot on what it is you're trying to assess, right? So, um, I'm not sure that there's one size fits all, but you've made a point. Let's just say I guess somebody comes up to me with a super new polymer, and boy, I'm excited about it. A big question is, will that actually propagate through my porous rock? And so one thing is you got your core, and to if you decide to inject at a fixed rate, look at the pressures, and if the pressure keeps going up, that means you got a problem. There's some kind of problem, and the problem could be face plugging, and you wouldn't know that unless you had at least one internal pressure tap. So by having an internal pressure tap, what you might see is um, continual increase in my pressure on the first section, and maybe it's stable on the next section. So, looking at the next section and saying, okay, that's a lot more representative than the first section. If I do see an issue with, okay, this is giving me something magic and I want to be sure of it, I really ought to get a relatively long core and look at multiple sections,
So
maybe more
when
than.
you say long, it's a foot long, like 30 centimeters.
Well, it I don't want to say it has to be a particular value. We've done it 4 feet long. Even one time we did 132 feet long. We just put a bunch of these things together. I mean, they weren't all one continuous piece of core, but we'd have a whole bunch of cores stuck together and have taps in between. And the whole question is the resistance factor that I see in the last section the same as in the middle section, as the same as is the first section? If I see that they're all the same, that makes me have a really good feeling like, okay, this stuff will propagate pretty well. That's
And
what I'm looking for.
and so there are two schools out there. The first one say I need to get pressure stabilization after two pore volumes, and some people say no, you need to inject 100 pore volumes or 1,000 pore volumes and make sure that there is no change in the pressure derivative over all these all the time. So what would be you think is the rationale behind, and what would you do in your case?
Okay, so a point is we have a lot of experience previously with polyacrylamide, xanthan, certain polymers. So one of the issues is, am I dealing with just a normal, everyday type of polymer, or am I dealing with some exotic new polymer? If it's an exotic new polymer, I got to do maybe more rigorous testing and be more careful about it. If I'm in pretty high permeability, we have real expectations that, all right, it ought to stabilize. If it's a normal polyacrylamide, it ought to stabilize and do not too problem. But if my goal is, I got to push the limits of this and I got to go to the lowest permeability I can, then I need to be more cautious about saying, all right, I'm not just going to say two pore volumes is enough. I need to be convincing myself that this stuff will actually propagate a substantial distance through my low permeability rock. So then I need to be injecting more pore volumes, maybe longer cores, more internal pressure taps. So, we have a space where a lot of work has already been done, and we have a space where people are pushing the limits. If you're pushing the limits, you need to be doing more and different experiments to convince yourself that that the polymer is really going to go into the formation, the distance that you need, and it's really going to provide the viscosity or resistance factor you need at that point. So that's the way you have to think of it.
I mean, maybe a couple of the problem I think I've seen sometimes is the people who push the limits with existing polymers and knowledge. So imagine that your polymer is stable up to 10 pore volumes, and after 15 pore volumes, the pressure starts to rise. Question is why? So there might be,
Exactly. That's the thing to ask.
yeah,
Why did it do this?
yeah. Is it
Right.
because they changed the polymer solution and the person that prepared it? Is it because there was something in the lab that happened? What's happening really? Because why it would go straight for 10 PV and then 15 nothing? And also for the people who push the limits, something I think is very important that is really changing and making polymer flood successful, even in cases where there are difficulties. The slight degradation of the high molecular weights in pumps and perforations will change the game for injectivity into the lower perm zones. And in the lab, what we have is something that is so pristine and I would say beautiful that, yeah, you have everything you can think of in terms of molecular weights. But if you just remove the portion which is at the very right side of the Gaussian curve, which are the very, very high molecular weight chains, then your injectivity will improve in I think in I mean it's not I think it's we've seen this in a great way, and that's probably the only time where you can use a screen factor in addition to your Coreflood to see the differences. So that's why I think it's difficult in the lab to really push the limits if you don't know what you're looking for, which is, yeah, as you were saying, testing a new chemistry, fine. But why in some case inject 1,000 per volume while 2, 5, or 10 will show you that it's going to work, knowing that the polymer might be a bit different in the field is always an interesting question, at least for me.
Yeah, I think you hit on it. Is we have expectations of what we want, and it's very important for you to decide what you want. Okay, like I want this viscosity or this resistance factor under these conditions deep in my reservoir. It's very important for you to decide that. And it's very important for you to say or to ask, is my laboratory experiment telling me that information? If I see something odd happening, you're exactly right. You got to ask the question, why is that happening? If I screwed up this experiment, is something happening here that is telling me that there's a red flag and maybe I need to be careful with this polymer? Or is it telling me that I need to do this experiment differently? Okay, so those are things that the guys in the lab always have to be asking themselves. And the field guys should be asking that too, right? Is like, are we sure what I'm seeing in the lab is representative of what's really going to happen in the field? That's absolutely
And
right.
so to continue on this, so cores with oil or without oil, and why? And for which test?
Yeah, and so again, that's depending on what it is you're trying to prove. If I just get a polymer and my initial question is okay, I see this viscosity, is the resistance factor that I see in my core more or less consistent with that? You know, I mean, uh, Guillaume Dupois just done a nice set of experiments where he said, okay, it looks like very consistently my resistance factor in the laboratory is maybe 30% higher than what I expect based on viscosity. That's okay. I mean, even if it's twice as much, I'm not going to get upset about that. But if it's 10 times as much or 5 times as much, there's a red flag. It says something's happening there that I don't understand, and I need to do something to try to figure out why this is happening. Right.
So how would the presence of oil, for instance, you published papers on this. So the impact of residual oil saturation on in situ rheology and on retention.
So we have, let's go with retention first. You would think that if the major adsorption ought to be on the rock itself. And if I start covering the rock with oil, maybe because it's a little bit oil wet, not quite totally water wet, or just the presence of the oil, you would conceptually think that ought to reduce the retention. And some people have just, picked up on that thought and then just not stopped, just said, okay, well, that's the way it is. And that's false. I mean, when you go back through the literature, you see very clearly there's just as many cases where polymer retention is higher in the presence of a residual oil saturation than it is without it, than the opposite of that. So yeah, that's not intuitive. You don't know why that's the case. Yeah, and so right now, counterintuitively, we cannot say that polymer retention is going to be necessarily lower in the presence of oil or lower if it's a more oil wet rock than if it isn't, right? And then that's just experimental observation. What it says is you got to do the test for your case and find out, right? That's
So, I mean,
right now that's where we're at.
I see two. So I have a follow-up question and a remark. My question is, for the people who are really sure about the wettability and the oil saturation and who have good protocols who can repeat the test, I think that's important. Also my understanding in the literature is, since everyone once again has different protocols, even to restore the oil, I mean the core with oil saturation, the aging time, cleaning with solvent or no solvent, etc. There might be here probably inconsistency just based on the protocol. So I don't say that the observations are not true. I just say that it would be interesting to really have something fixed in terms of protocol and see if we can repeat. And my follow-up question would be, would it be the same in carbonates, given the charge of the surfaces, the presence of calcium, magnesium, and the wettability, which is, which is very often more on the mixed intermediate or oil wet in carbonates? Because I've read papers, good or bad, but in some recent GIPs, people have noticed that in carbonates with oil, the retention of polymer was lower than without oil.
And I think that's the key thing, is to actually do the experiment and see it. We have a lot of concepts out there that have been thrown out because somebody thought, well, this is a good idea many, many years ago. And those concepts haven't turned out to be correct. For example, the concept is carbonates tend to be more positively charged than, and whereas clastic rocks tend to be negatively charged. And if I got an anionic polymer, it's going to be repelled by the anionic charge on a clastic rock, and it's going to be attracted. And therefore, okay, but I mean, there's massive flaws with that argument, right? Now, so number one, yeah, okay, maybe they found the case of the particular carbonate charge. At that particular circumstance, they could measure it as being positively charged. But all of these systems in the Middle East where they're using the going after the carbonates, they're high salinity and high hardness. So they're, if there's any charge type of interaction, you've got so much screening taking place from all this salt that's there. You have no idea what's going to really happen on that. So doing that simplistic idea is simply not going to work. The only thing you can, the only thing you can really do is go out and measure it for the particular circumstance. So.
But I see your point. So maybe it's not the fact that there could not be such interactions, but that there are other factors maybe already preventing even these interactions with the rock and even the rest. And we see results and get an interpretation which is based on other mechanisms that the one we are trying to investigate, if I understand basically correctly.
Yeah.
So retention. So again, some experiments we've made in the past were showing lower retention in oil with oil saturation compared to no oil. But again, depends on the geology and the rest. But what we've seen consistently, and what you've seen also, is the impact of ATBS on retention. So
yeah, now that is really interesting. So I mean, you could
so
argue that a couple of ways. You could say, maybe we haven't done enough tests, and then that would be a legitimate argument. But the tests that we've done and you've done and a number of other people have done have consistently said that at least on clastic rocks, the presence of the ATBS is having a surprising effect. Even like at Milne Point, even having something with 5% ATBS in it had really quite substantially less retention on the Milne Point type of material than the polyacrylamide, and that could have a massive economic value to it. So you could legitimately argue that we need to do more tests in different circumstances, but right now that's a very positive indicator. Yeah.
Just something I remembered. So you mentioned that in situ rheology using the viscosity at Newton and plateau was important. And of course, when you change permeability, change velocity to account, to recalculate viscosity. But when you come to retention, that normally takes into account adsorption and some, entrapment linked to the first the flow features plus the size of the polymer. But so wouldn't we expect to observe higher resistance factor in lower permeability with the same polymer because just of the hydrodynamic retention? Or is it something that will be anyway, I would say, that will disappear as soon as you break a little bit the molecules?
Yeah, so the thing is trying to get everything else being equal and then looking at an
Yeah.
effect. And so if we could make everything else be equal, we certainly have, I mean, people have seen for 50 years consistent trend that, if you're above a certain threshold type of permeability, your resistance factors are pretty much constant and consistent with viscosity. And once you start getting below that threshold of permeability, your resistance factors, residual resistance factors, and your polymer retention tends to go really high, really fast. So, and which is consistent with the plugging type of behavior, which is consistent with saying that polymer is just not going to propagate through that kind of rock. So don't kid yourself, right? So that's a general truism that most people have seen, right? Yeah. Okay.
So retention, so there is a threshold below you have a lot of changes into retention. Coming back to retention procedures, so um, are you using, you are using more dynamic retention tests. So what's your basic protocol? Is it the two-front method with the iodine in between and a large flush of water, or just tracer and polymer? So what are you using
So
most?
what I have been using is the two bank test. So it's a polymer with a tracer in it, and then a very large bank of water in between to flush it, and then come back with another tracer and polymer. And a lot of people have pushed that for a lot of years, and I think there's a lot of positive parts to it. I do need to mention recently, well, within the past few years, Matt Dean had come out with this test where you inject um, the polymer with a tracer. First, you have the core at kind of a residual condition, and then you come in with the polymer with the tracer, and then you come in with a little higher concentration of polymer, either with another tracer or maybe with no tracer. And and conceptually, that has some real positive features to it. I mean, then you don't have to do this massive, long experiment. You can just do, because you got the reason we had to do that two bank test with massive amount of water between it was because of the unfavorable mobility ratio when water is displacing polymer, and a lot of people have done that test wrong and not injected enough. Matt's test gets around that problem by always having a positive or a favorable mobility ratio. So you go from basically water flow to a certain level of polymer concentration flow to a little higher level of polymer concentration. So you don't have to inject anywhere near as much fluid or polymer bank. You need to get stabilization of both of your banks, absolutely. But I've been playing with that, and I have to admit I like that test. It does make the test a lot easier. And so far, I mean, I need to do a lot more testing with it, but so far, I'm happy with the results of it. So that might be something that is of value to pursue some more. Certainly, some more tests. Again, in talking with Matt, he's got some surprising results that I didn't expect and that just aren't intuitive. and we need to understand why that occurred. Is it because of the test, or is it because of some other odd thing? But initially, I'd say I'm kind of encouraged with that test. I think it might have some value to it.
And so something you've observed and published on recently about the tailing phenomenon. So can you explain a little bit what you have observed and what you think are the reasons behind?
Well, so the convention, the normal convention that most people have is I put polymer in a bank of polymer, and a little chunk of rock grabs all the polymer it wants, and then until it's satiated. And a lot of our simulators, maybe most of our simulators, assume that too, basically, that I'm going to take all the polymer I want, and then what's left goes on. But what that effectively means that what goes on, if my gridding isn't too coarse, is going to be basically the same concentration as what I injected, right? Um, and so that means when your polymer breaks out in an experiment, you should get a fairly sharp breakout. Let's say your tracer comes out first, and then your polymer comes out later at a little higher pore volume value, but they both end up stabilizing quickly at the injected value. So that's the ideal, and that's what's assumed in fractional flow calculations and what's assumed in most simulators. So then you basically get your polymer retention by that area difference between your tracer bank and your polymer bank. What we saw, to some surprise there, is that the polymer broke out with the tracer, basically indicating no polymer retention at all. But the polymer didn't come up all the way to immediately to follow the tracer to get to 100% concentration. Instead, maybe I got up to about 70% of the injected concentration, and then my polymer concentrations just tailed, or just gradually increased over the course of maybe the next 5 pore volumes before it finally reached. So there was this tailing effect, and a big part of what we did was trying to figure out why that happened, and I think we got it kind of figured out. But the other part of it is the practical significance, and it has a substantial practical significance of it, because the practical significance is when you inject it, the nice thing is the polymer is going at the same rate as the tracer. So it says that polymer is not being impeded in propagating through the reservoir. That's good, because you get your polymer in there, contact the oil, and get it starting pushing. That's a really wonderful thing. That's more than 50% of the way I want to be there. But the problem is, I had an idea that maybe this is going to be, I don't know, 30 centipoise, let's just say, but it's not giving me 30 centipoise because it's only 70% of that concentration. Maybe it's only 20, 25 centipoise. So what it says is, the good news is I'm propagating fast. I'm not getting any inhibition of the movement, but I'm not getting the concentration that I needed. So a simple way to get around that, of course, is to over design, and instead of injecting what I think is 30 centipoise, inject 35 or 40 centipoise, so that I get the mobility that I want in the reservoir. The fact that it's tailing out, from a practical viewpoint, I'll never actually see deep in the reservoir. I'll never see that 100% concentration, just because of that tailing effect. So it's been a really interesting and unusual property. I'm starting to hear people more and more tell me that they're seeing that as well.
So, but you didn't mention the mechanism behind. So you said you have it figured out.
Yeah, we figured it out after a lot of work. We figured out this is due to the presence of the clay illite. We also see it with kaolinite. It shows the same type of effect. And the more kaolinite, the more illite you have, the more you're going to see this type of effect. So, it is going to be something that's more important in clastic type of reservoirs, where you have significant clay contents of those features. It is, we tested a lot of different things like polymer molecular weight, salinity, divalent ion concentration, ATBS concentration, velocity, permeability, a lot of different things. And I'll just say we have a series of 3 papers. The one that, if you're really interested in the ultimate mechanism on that, which probably not all people are going to be, but go to SPE paper 212946.
Yeah, I've said I've read them, but I don't remember the number, so it would be
Yeah,
good to.
I just have to see it right here. So anyway, that's paper that kind of goes into the detailed mechanism, which and goes into a lot of detail of why we came to that mechanism. So yeah.
So we mentioned shear viscosity, curves, degradation, Corefloods. So maybe anything that's left that we forgot for the lab part. So
Well, I'm sure there are a lot of things, and the reality right now is we have very much differences of opinion throughout the industry of what's an important test and what's not an important test. Sometimes those differences are legitimate just because one reservoir has different issues and problems than another reservoir. So I mean, we have to realize that's maybe one reason why we're never going to get one protocol is the only one that should ever be used. But there also are things where people are making big mistakes by placing too much emphasis on a particular test as well. We have both problems out there, and I guess we just need to fight through them to resolve them. Yeah.
and just maybe a last word, something we forgot is what about oil recovery testing Corefloods? Why would you use them, and what value would they bring to your case? So you mentioned the design of the right injection viscosity in that case to with using the real perm. But I know quite a few people who use the oil recovery test as input for the simulation or for history matching to try to build a business case. So what's your view about the oil recovery test?
Yeah. Okay. So I would separate it into two parts. The part of building a business case, um, a lot of that has been misused, and I understand it. I mean, if your primary funder is a hedge fund operator or a banker or a lawyer or a doctor or something who just has extra money to kick in and they just want to see something like this because they don't understand the process. Okay, it's probably not of much more value beyond that. But in a real place that really is of value is like in these Canadian floods where people want to inject um, relatively low viscosity materials. Like I said, the really good example is cactus lace, like a 1600 centipoise oil. And we did a series of oil displacement experiments, one with just water displacing the 1600 centipoise oil, one with 5 centipoise polymer, another one with separate test with 15 centipoise, a separate test with 25 centipoise, a separate test with 50 centipoise, a separate test with 200 centipoise. And what we showed is we got improved recovery up to 25 centipoise, and then we didn't see any additional improvement beyond that. And the value of that test is it's telling us that the effective endpoint relative permeability to water is a lot lower than most people would think. It was like 0.03, and we were perfectly justified in putting in a 25 centipoise polymer to displace that 50 cent or 1600 centipoise oil. Whereas without that, you would have said, well, if my endpoint is really 0.1 or 0.2 or 0.3, I should be injecting a whole lot more polymer than that. So that's the value. I mean, if you can definitively know that 1,000 part per million is going to give me just as much oil recovery as 2,000 part per million oil recovery. Obviously, you're saving a whole lot in polymer costs. So, that has a massive both technical and economic value in knowing that.
So, I mean, we'll conclude the talk. Some things I would like to discuss maybe next time about the use of pressure drops instead of history matching them, and maybe the fixed pressure drop Corefloods and the use of even the pressure curves and derivatives to understand retention or mechanisms. But so if you had to put together 3 or 4 bullet points about this discussion, so what would you like people to remember about the lab test and polymer selection and characterization?
So number one, the simple thing of getting that viscosity versus a lot of, conditions relevant to your reservoirs, a good simple thing that's we've done forever, and it is of high value. Number two, whatever test you pick, we got different conditions for different reservoirs. You have to say to yourself, what are my reservoir conditions? And like I say, low permeability or low temperature, low salinity, high permeability, clastic reservoirs is going to have a whole lot different criteria that I have to get worried about than low permeability carbonates and high salinity, high temperature type of reservoir. So we have to know where we are and asking the question, what is it that I really need to know? Is it stability? Am I not worried about stability? Is it effective resistance factor deep in the reservoir under these conditions? Is it, will my polymer really propagate under these conditions? Deciding which of those, and then make sure your test is designed to give you a good answer to that. Okay.
All right. Well, so thank you very much, Randy,
Thank
for this
you.
session.
We'll talk with you
And
next time then.
yeah, and hopefully another time on a follow-up topic. So thank you, Randy. Have a very, very nice day and see you next time.
Okay. Thank you.